Namaste everyone. Let us start Fourier analysis now. In the last chapter, we have seen how we could do represent a signal with the help of basic signals. If some signal is given to you, you can represent it in terms of unit step signal. You can represent it in terms of ramp signal. You can represent it in terms of the uh, impulse signal, like that. So ultimately I can say that we were able to present a signal with the help of basic signals. Now we are going to a back level, means previous level or ancient level. We are going to study an ancient analysis which was very useful and which is useful now also. The Fourier series was developed a long ago in something about 1700, 70 or 80 around, at the time of Fourier, the time of French Revolution. So it is around 300 years back. Okay. It's around 250 years back it was discovered, and at that time these signals like impulse signal, ramp signal, unit step signal, these signals were not in practice. Only sinusoids were in practice. So that time the idea was to represent a signal with the help of a sinusoidal signal. Later on, the concept converted to represent the signal with the help of even the complex exponential signals also. Okay, so later on this complex exponential were also became popular instead of the sinusoidals that were. So that was the idea. You know that this representation in sign terms or importance of periodic signals is from very ancient time in our country. In the ancient time, our astrologers of our country like Aryabhat, Varahamihir, Susrut, and Panini and Latadev, they were they were using it. They were using the sinusoidal signal. They were using the representation of periodicity, rotation of Earth, rotation of Moon, rotation of different grahas or different uh, solar systems. So for studying all those things in our ancient India, there was a system. They were using the sinusoidals. They were using the periodic systems. There was the concept of transformation also. So, but the science was astronomical. There was no data science like things or something like data science, data analysis or signal analysis at the time, because sensors were not there, and this modern technologies of digital signal processing was not there. Therefore, they used to uh, use it for the astronomical analysis or prediction of future, astronomy, astrological things also. Nowadays, we have in later on we had one scientist. Uh, his name was Bernoulli. Bernoulli did experiments and also predicted one that there are normal modes in a vibrating string. If I vibrate the string, so in this vibrating string, there are modes. You can see in this video, one student is holding a string strong in a strict hand, in a fixed hand, and the professor is producing the modes. So in 1753, Bernoulli had given this idea to represent strings in the form of the modes. You can see here the this is given in the Oppenheim book, figure number 3.1. This picture is taken from there, and it is showing that how a motion of string can be converted to the vibrating string. But the problem was that Bernoulli was not able to convert it in a mathematical form. So therefore, his ideas were not widely accepted by the scientists of that time, by the physicists and mathematicians of that time. Later on, a very famous person, Fourier, came, and the Fourier had given the idea. He was working for the heat transfer problem, and he had represented the signals in the by using the sinusoids. He had given complete mathematical expressions for that. So I can say Fourier means very renowned personality at that time. Fourier, Laplace, Lagrange, and Drichlet, they were famous at that time. So Fourier was working on the heat transfer and law of conduction, like that. So and that time only he had given these equations of Fourier analysis. Okay, so the story, the Fourier, I will tell you a story of the Fourier. Fourier was a physicist actually by nature, but when he uh, went, means he had one, he faced the problem of French Revolution. So at that time, uh, he met with the Napoleon Bonaparte. You know Napoleon Bonaparte? Yeah. Waterloo War, you must be knowing. So Waterloo War, where the Napoleon was died. Okay. So before that, I say he was with the Fourier, and Fourier was one of the important person for the Napoleon, because Napoleon was also interested in the science and technology and developments of scientific theories, like that. Therefore, Napoleon took uh, him as a friend. So both Napoleon and Fourier are here. You can see the right side is Fourier, and left side of the picture, in the picture, that is Napoleon. So they have to leave France at the time of French Revolution, and they had to travel. And over the voyage, and while traveling, when their ship was moving, so at that time, motion of ship
Sail through a
had been
bumpy,
observed
turbulent,
by these
ever-changing ocean or
persons,
sea.
and they observed
The
that
ship's
when the
motion
ship is moving, that motion, linear motion of the ship, is being converted into the sea waves. Those sea waves strike into the mind of the Fourier, and Fourier converted those sea waves into the mathematical form when he came back to his home. So you can see the story in detail when you study Oppenheim book. So in this figure 3.3 in book, it is shown that this ship, this motion of the ship, the wavelength waves of are coming from the out of the ship, like motion of the ship. Because of the motion of the ship, you can see in this figure. Okay, so you can see that this the sinusoidal signals are very important because they are periodic in nature. They can represent the electricity coming in our homes. In everywhere, electricity is represented with the help of sinusoidal signals. Motion of Earth, motion of Moon, and there are many periodic signals that all can be represented with the help of sinusoids. And the special representation of sinusoids is complex exponential signals, which have both sine and cosine together in one signal. These are very useful for representation of AC electric currents, LC resonating circuits behavior, harmonic motion of the mechanical systems, of spring loaded systems, like that. So the simple harmonic motion going into these systems can be represented with the help of complex exponential signals. Acoustic pressure in the musical tone and music systems is also represented with the help of these systems. So this is very useful phenomena. Means this is very these are very useful. Complex exponentials are very useful in nature. Okay, so let me take you to one. Okay, that do some settings. Okay, then let us see the next one. What? Okay, Fourier series came into the picture. Okay, but the Fourier series was not accepted by the scientists of that time. So the Fourier, after his work, after 25 years of his work, his theories was accepted by the scientists. When Drichlet was had given conditions of usefulness of Fourier series, मीन्स फोरियर सीरीज कब यूजफुल होगा, कब उसको यूज कर सकते हैं, ये ड्रिचलेट ने बताया. जो अपोजिशंस थे उस टाइम के साइंटिस्ट के, ड्रिचलेट ने सॉल्व किए. तो ड्रिचलेट कंडीशंस ऑफ फोरियर सीरीज आर वेरी इंपॉर्टेंट. फर्स्ट कंडीशन of Drichlet, or first condition of Drichlet is that the function should be well defined, single valued, and function should have a finite average over the period, and also this function should be true, means the function should be absolutely integrable. Integration of function over a one time period should be less than infinite. That means function should be absolutely integrable. Okay. Yeah, here I have given one example. One square wave is given. So this is square wave. You can see it is well defined. It have one value and zero value here, one value here and zero value here, and it is single valued, means at every time instant there is only one value of this signal, and it have finite average. Average is zero, that is finite over the time period. But I have here second example also. In this second example, Fourier series is not valid. Why? Because at same instant there are two values in this signal. One value is positive, one value is negative. So therefore it is not single value. As it is not single value, therefore Fourier series of this function is not possible. Is this okay? Have you all understood this point? This is an important point to note. That there are signals for which it is not, Fourier series is not valid. One more example is here. This is xt equal to 1 by t for one time period. So you can see here the average value of means the value under the curve in the time period, it is infinite. Therefore, area of the curve will be infinite, and the function will not be absolutely integrable, and the average value of the function will be infinite in the particular one time interval or one time period. Therefore, the Fourier series for this is not possible. Is this okay? Okay, then let's go further. The second condition for the Fourier series to be applicable was given by Drichlet. That was that there should be a finite number of discontinuities over a time period. There should be finite number of discontinuities in the time period t. Now, what do you understand by discontinuity? If I have a sinusoidal signal, how many discontinuities are there in this signal? There are zero discontinuities, because there is no point where the value is not known, not definable, because at every instant value is fixed. Okay, therefore there are no zero number of discontinuities. Okay, it can be zero. Finite number means it can be zero also. Okay, let's go further. Okay, let's go further. Discontinuities, here you can see here there are discontinuities. Let me show you. See, in this there are discontinuities. Where is discontinuity? It is shown here. Here, this point is discontinuity point where value cannot be defined. Not this one. This one. At same instant, value is 0 and 1 also. But in this triangular wave, there is no discontinuity, and in this there is discontinuity. If discontinuity are finite, then there is no problem. But if the discontinuity are infinite, at that time we say that the signal cannot have Fourier series. Okay, so this is the example where there are infinite number of discontinuities in a single time period. What they say, that the signal starts, goes down, then signal goes down. It became step is becoming smaller as it is moving further. It will complete infinite steps before going to this point. So this infinite step will have, every step will have one discontinuity. Therefore, infinite discontinuities are there in this particular signal. Okay. Therefore, this is the Fourier series will not converge for this signal. Converge means Fourier series is not applicable for this particular signal. This okay. Next one, third condition. I had here one. Third condition is that FT must have finite number of maxima and minima. So how many maxima minima in this? 1 and 2. 1 maxima, 1 minima. Okay. And but here you see that in one time period there are infinite number of maxima and minima in this signal, because this signal is becoming closer in one time period. Therefore, there are infinite number of maxima and minima, and this infinite number of maxima and minima, infinite maxima. Okay. So because of this infinite maxima and minima points, this signal cannot have Fourier series. Is it okay? Now practice, for your practice, here some questions are given and you can note it down and you can write answers of these questions in the comment box of the video for all five. For first, whether Fourier series is possible or not. For second, whether Fourier series is possible or not. So you have to write A, possible, B, not possible, C, not possible, whatever is coming. Not write, do not write like this. One more question I am giving here. One signal is like this. Okay, this is one, this is two, this is three, this is four, and this is zero, and before zero also same minus one. And okay, so this kind of, this is two, three. Okay, this kind of signal is available. So for these five questions, you just think about based on our discussion whether Fourier series is possible or not, and write the answers in the comment box of this video. Okay, thank you so much. Thank you all.